Hello everyone, this is Rajiv from Seed Academy. Up to now we had completed 3 units in low power design subject. In this session I would like to explain the 4th unit of low power design, which is a leakage power reduction technique. This unit consisting of the following topics: leakage power reduction technique, multiple threshold, transistor stacking, input vector control, sleep transistor, variable threshold technique, multiple threshold technique, dual threshold CMOS using multiple thresholds, transistor stacking using self reverse biasing, leakage control stacking, and input vector control, influences on subthreshold leakage, gate leakage and BT, and total leakage, and finally the sleep transistor technique using multiple threshold CMOS. For this unit I had prepared a presentation which gives a clear idea about each and every topic in this unit. The presentation consisting of this following topic: introduction to the leakage power, transistor leakage mechanism. In a single NMOS transistor there are various types of leakage currents. There are mainly 6 types of leakage currents. All these 6 types of leakage currents can be explained in the next slide. After that, leakage power reduction technique. There are mainly 2 types of leakage power reduction technique. One is at process level, second one is circuit level. Process level means before the fabrication, in how many ways we can reduce the leakage power of a transistor. In 4 ways we can reduce the leakage power of a transistor. All these techniques explained in the next slide. But once the fabrication is done, in how many ways you can reduce the leakage power of a transistor while using the transistor in circuit. Means there are 6 circuit level techniques to reduce the leakage power of a transistor, which are transistor stacking, multiple threshold technique, dual threshold CMOS, variable threshold CMOS, dynamic threshold CMOS, double gate dynamic threshold SOE CMOS. All these techniques I will explain in the next slide. Okay. Introduction. As we already known that CMOS power dissipation is a combination of dynamic power as well as static power in active mode of operation. When the transistor is in active mode, the power dissipation is mainly due to the dynamic power as well as static power. Again, the dynamic power is a combination of both switching power as well as short circuit power. Switching power is the power consumed when the device switch. It means when the device is on and when the device is off. The power consumed when the device is on state and the power consumed when the device is in off state. And the short circuit power is the power consumed when the both PMOS and NMOS in on state. It means there is a short circuit path between VDD and VSS. The power consumed when the short circuit path arrives in the circuit is called short circuit power. That will account in dynamic power. So when the device in active state, when the block in active state, there are 2 types of power dissipations will occur. One is dynamic power and second one is static power. When the device in off state, it means standby mode. Standby mode means it is not in off state. It is still in sleep. It means the sleep mode. The background operation can run. In standby mode, the power dissipation is mainly due to the leakage power of transistor. So power dissipation is mainly due to the leakage current. So let us quickly read this each and every point in this slide. For a CMOS circuit, the total power dissipation includes dynamic and static components during active mode of operation. In the standby mode, the power dissipation is due to standby leakage current. Dynamic power dissipation consisting of two components, as I already explained. It contains the switching component, switching power, as well as short circuit power. Switching power is due to charging and discharging of load capacitance. It means that when the PMOS is on, in CMOS circuit, the capacitor is charged to VDD. When the NMOS is on, the capacitor is discharged to ground through a NMOS transistor. So power consumption in dynamic power dissipation is due to mainly these two components. One is switching power, the other one is short circuit power. So the static power of a CMOS circuit is determined by the leakage current through each transistor. In the previous slide, I had explained there are 6 types of leakage currents that should be happen when the device is on state or off state. So to find the total leakage of a transistor, we need to account all these 6 components. So the leakage power is P leakage. P leakage is equal to I leakage into supply voltage VDD. I leakage is a combination of cumulative of all leakage currents. There are possible 6 types of leakage currents in a transistor. In the next slide, I will explain all these 6 types of leakage currents. So I leak is a combination of cumulative addition of all these 6 types of leakage currents. So I leak is a cumulative leakage current due to all the components of leakage current. So all the components means there are 6 components of leakage current in an NMOS transistor or a PMOS transistor. I will explain all these components in the next slide. As you already know that the current CMOS technology is working on 1 volt power supply. Supply voltage is 1 volt. Previously it is 5 volts. It means that supply voltage is reduced 5 volts to 1 volt because of technology scaling. It means that previously the shifter manufactured with 90 nanometer technology. Now the current shifter running with 22 nanometer as well as 14 nanometer. As the technology is scaling down, we need to reduce the supply voltage also. As the supply voltage is reduced, in addition we need to reduce the threshold voltage of MOS transistor. Reducing the threshold voltage means there is a cause of subthreshold leakage, and there are more problems with subthreshold current. So reducing VTH means you are suffering from leakage. As the VTH is reduced, it means that subthreshold current is increased. As the VTH is high, subthreshold current is decreased. So leakage current is mainly depends on VTH. It primarily depends on VTH. Okay. Leakage power is a significant component in total power consumption in both standby and active mode of operation. Okay. So I had mentioned the points which are important to us in the slide. You can easily understand this point, and you can easily understand the concept also. Okay. So now I would like to explain the transistor leakage mechanism. So I am taking an example. I am taking an NMOS transistor which consisting of a P substrate and 2 N plus. One is source and other one is drain. And this is SiO2 oxide, SiO2, and this is a polysilicon. In this transistor there are 6 types of leakage current that should be arrived when transistor is on state, both off state also. Both in on and off state there are 6 types of leakage current that should be arrived. So what are those 6 currents? I will explain. Just follow the figure. I1 is a current due to the reverse biased PN junction leakage. Where is I1? This is I1. I1, there is a reverse bias connection because this is a P substrate and which is a grounded, and this is N place. So there is a formation of PN junction between P and N, and it is reverse biased for operation of NMOS transistor. Again, there is one more diode forms a reverse bias with source. This is source, this is substrate. As source is ground and substrate is ground, the effective potential constitutes to this diode in reverse bias. So as we already known that diode conducts when it is in forward bias, and it will not conduct when it is in reverse bias. But still there is a minority carrier current due to the leakage current, that is called reverse biased PN junction leakage. I1 is the current due to the reverse bias of both PN junctions. As the PN junction is reverse biased, ideally there is no current, but in practical there is some leakage current due to the minority carrier concentration in both P and N. This minority carrier concentration is because of diffusion current, because minority carriers can have tendency to diffuse from higher concentration to the lower concentration. Similarly, minority carriers means both electrons and holes in P and N respectively. So minority carriers can have a tendency to transform from high concentration to low concentration, and because of concentration ingredient. Okay, there is some leakage current because of this diode, the diode formation, reversed biased diode formation. So this is I1. What is the second current? Current I2. I2 is because of subthreshold leakage. As we already known that MOSFET can operate in three regions of operation. One is cutoff, second one is non-saturation or linear region, third one is saturation. For operating this transistor in three types of region, we have some operating conditions. What are those operating conditions? As VGS is less than VTH, it means that there is no channel formation, the transistor is in cutoff region. Second condition is VGS is greater than or equal to VTH, and the VDS is less than the effective gate voltage, that is VGS minus VTH. VGS minus VTH is the non-saturation region. For saturation, it is greater than or equal to, and this condition. We already studied this concept in first semester. It means that there is no current. It means that there is no current or no channel when VGS is less than VTH. It means that there is no formation of inversion layer in the channel. So while forming the channel, there are three types of regions we already studied. One is accumulation region, second one is depletion region, third one is inversion region. Accumulation region means there is no gate voltage is applied to the gate. It means that VGS is equal to 0 or negative. The channel is accumulated of fully positive carrier, that is called accumulation region. As you start increasing VGS, the channel is depleted of carrier, that is called depletion region. As the VGS exceeds the threshold voltage of a MOS transistor, there is a formation of inversion layer. It means that channel is fully inverted, that constitutes current. It means that ideally there is no channel formation, there is no inversion layer, then VGS is less than VTH. But in practical, there is a weak inversion is there that constitutes to subthreshold leakage. even VGS is less than VTH, that is the second current subthreshold leakage. Subthreshold leakage. I will explain each and every current component, leakage current component in the next slide with a good explanation and good matter in the slide. Okay. Third current is offside tunneling current. Third current is offside tunneling current. And fourth one is gate current due to odd carrier injection. Because of odd carriers in the channel, there is a current passing from gate to the channel, that is the gate current. Fifth one is I5. I5 is the GIDL, gate induced drain leakage. The current I5 is the gate induced drain leakage. This concept I will explain when I am explaining this leakage current component. And sixth one is punch through current. This is the current due to punch through. What is punch through? How the current is flowing? I will explain in the next coming slide. So basically, if you look at the transistor structure, there are six leakage current components are present, which are there due to the I1. I1 is the reverse biased PN junction leakage current, which is because of there is a PN junction formation between N plus drain and P substrate, N plus source and P substrate. If that reverse biased PN junction, that constitutes a leakage current, that constitutes the I1 leakage. Second one is I2 is a subthreshold leakage, purely based upon threshold voltage and VGS, applied input voltage VGS. Third one is offside tunneling current. There is a possibility of tunneling of electrons from substrate to the gate and gate to the substrate because of potential barrier at the SiO2 interface. This is Si. This is SiO2. Potential barrier at SiO2 interface. There is a possibility of tunneling of electrons from gate to the source, gate to the substrate and substrate to the gate, that constitutes offside tunneling current. I4 is the odd carrier injection, means electrons, high energy electrons can inject into the gate because of tunneling, that is called I4 current. I5 is the GIDL, which is gate induced drain leakage, and I6 is the channel punch through current. Current I2, I5, I6 are off state currents. I2, it means that when VGS is less than VTH, the transistor is in off state. So I2 is in off state leakage. I5, similarly I5 is also a off state leakage current, and I6 is the current due to the punch through. What is punch through? When it is occurred, I will explain in the next slide. I2, I5, I6 are the off state current leakage mechanism, where I1 and I3 can occur both in on state and off state. The current I1 is due to the PN junction of N plus drain with P substrate. This can occur in both when the transistor is on state and when the transistor is in off state, both on and off state current. Similarly, I3 is also, tunneling can occur not only in the off state but also in the on state. Okay. I4 current can occur in off state, but more typically occur during the transistor bias state in transition. When the transistor is biased to operate in on state or off state, depends upon the bias condition, the I4 can likely to be happen. Now let us look at each current component clearly. Okay. The first current component is the reversed biased PN junction current. Reversed biased PN junction current. Here I am taking an example of CMOS inverter, CMOS basic circuit. For this I am designing my CMOS with N-well process. So basic is P substrate. In P substrate N device is formed. In N-well P device is formed. So there is a possibility of source and drain with respect to the substrate. There are reversed biases in normal operation. So there are 4 diodes formed: diode 1, diode 2, diode 3, diode 4. Again there is a possibility of one more diode which will form between N-well and P substrate. So when for normal operation all these diodes are to be in reversed biased. So for normal operation of a CMOS inverter, these formed diodes are reversed biased with respect to the substrate. Then only your device will work. So we all think that when these diodes are in reversed bias, ideally there is no leakage current. But in practically there is a possibility of leakage current due to the reversed biased condition of these diodes. So current due to this reverse biased PN junction is called reverse biased PN junction current, which will one first leakage current component of CMOS transistor. Okay. Let us quickly read the points in the slide. Source or drain form a reverse bias with the substrate, as I already explained. Depletion regions are formed. When they are reversed biased, it means that depletion regions are formed. The depletion region width is high when it is in reversed bias. So reverse biased PN junction obviously causes a leakage current due to the minority diffusion. As I already explained, in reversed bias the current is due to the minority carrier, and that current is because of diffusion, not the drift current. Drift current is the current due to the application of electric field. Here we didn't apply any electric field. So due to the concentration gradient, there is minority carrier tends to transform from higher concentration to lower concentration. So the current due to this diffusion current is called reverse biased PN junction current. This is the first leakage current component of CMOS transistor. If there is heavily doped drain and substrate, chance of BT-BT tunneling. Okay. What is BT-BT tunneling? I will explain. BT-BT means band to band tunneling. We already studied there are 2 types of bands: valence band and conduction band. In between these two bands there is the energy gap, there is a forbidden energy gap. The current conduction occurs only when electron transfer from valence band to the conduction band. Then only the current conduction is possible. It means that we already studied when we studying about the materials, 3 types of materials: semiconductors, metals, insulators. Semiconductors is the energy gap is 1 electron volt. 1 electron volt. If you had applied energy exceeds this 1 electron volt, the electrons from valence band can shift to the conduction band. This constitutes a current. So what is band to band tunneling? It means that we already know that N plus are heavily doped drains and P substrate is lightly doped. If there is heavily doped drain and substrate, if the substrate is also heavily doped, we already know that drain is heavily doped because of for heavily doped drain we mention with P plus, we mention with plus. Heavily doped means plus, lightly doped means there is no plus, it means lightly doped. If both P and N, it means if both substrate and drain both are heavily doped, there is a chance of tunneling of electron from substrate substrate to the drain, that constitutes a leakage current, that is called band to band tunneling. Tunneling of electron occur when an electron transfer from P substrate to the N plus drain, that is called BT-BT tunneling, band to band tunneling. So in the next slide I will explain what is BT-BT. So this is my P side. P side means this is my P substrate, and this is N side. It means that this is my drain. As I already explained, BT-BT occur only when both P substrate as well as drain both are heavily doped. For this I mentioned both P and N, not P plus or N, or not P or N plus. So it means that both are likely doped, means both are samely doped. It means that both are heavily doped. So when both are heavily doped and high electric field, it means that the electric field is 10 power 6 volts per centimeter across the reverse biased PN junction, causes a significant current to flow through the junction. Due to the tunneling of electron from the valence band of P region to the conduction band N region, there is a band to band tunneling occur. Okay, band to band tunneling when it is occur, when both drain and P substrates are heavily doped, and this heavily doped, it generates a electric field. That electric field is 10 power 6 volts per centimeter. If this electric field can have electrons tunneling from P side to the N side. This is one electron in P substrate can tunnel from P to N. It means that tunneling to occur, the total voltage drop across the junction, has to more than the band gap. This is a P, this is N. P means P substrate, N is means N plus drain. The voltage drop across this junction, when this is reversed bias, it means it will drop some voltage, then only the reverse bias occur. The dropped voltage exceeds the energy band gap of this junction, then only tunneling will occur. So band to band tunneling occurs when the voltage drop across the PN junction, reverse biased PN junction, voltage drop across the reverse biased PN junction exceeds the band gap energy of the junction, then only BT-BT tunneling will likely to be occurred. That's why I explained the BT-BT tunneling when I am explaining about I1 current. So BT-BT tunneling current occurs only in I1 current. So for BT-BT to occur, what are the conditions? The both P substrate and N plus drain both are heavily doped, and the voltage drop across the reverse biased PN junction exceeds the band gap energy of the junction, then only and BT-BT tunneling will likely to be occurred. So when I am explaining about reverse biased PN junction, this is the first component of CMOS leakage mechanism. Along with reverse biased PN junction, there is a possibility of band to band tunneling current. This band to band tunneling current occurred only when both drain and P substrates are heavily doped, and the voltage drop across the reverse biased PN junction can exceed the band gap energy of the junction, then only the BT-BT tunneling will likely to be occurred. Now look at the second current component of leakage component. So second current component is due to the subthreshold leakage. Subthreshold leakage. As I already explained, when I am explaining this subthreshold leakage, ideally there is no inversion layer when VGS is less than the threshold voltage of MOSFET. But in practice, there is a weak inversion is likely to be occurred. That weak inversion contains both majority and minority carriers. Minority carriers can tendency to diffuse from higher concentration to lower concentration. Even though the applied input voltage VGS is less than the threshold voltage of MOSFET, there is some leakage current is due to the minority carrier concentration in the channel because of weak inversion layer. Once again I am repeating. Ideally there is no inversion layer when VGS is less than the threshold voltage of MOSFET. But in practice, still even though VGS is less than the threshold voltage of MOSFET, there is a weak inversion layer. This weak inversion layer contains both majority and minority carriers. Minority carriers can tendency to diffuse from higher concentration to lower concentration even though the VGS is less than the threshold voltage. So this constitutes a current that is called subthreshold leakage current. That is the second current component of leakage mechanisms of transistor. Leakage mechanism of transistor contains six types of leakage current. I explained the first leakage. First leakage is due to the PN junction leakage. In this slide, I am explaining the second type of leakage. This is a subthreshold leakage I2. I2 is mainly because of minority carrier in the channel. Even though VGS is less than the threshold voltage of MOSFET, this carriers can tendency to diffuse from higher concentration to lower concentration even though VGS is less than the threshold voltage of MOSFET. Now let us quickly read the points in the slide. This I already explained. Subthreshold leakage or weak inversion conduction current between the source and drain in a MOS transistor occur when gate voltage is below VTH. In the weak inversion, minority carrier concentration is small but not zero. Previously I explained, in weak inversion there is a minority carriers are there practically, but ideally there is no minority carrier. So this minority carriers can diffuse from higher concentration to lower concentration because of concentration gradient. Let us consider that source of the N channel MOSFET is grounded and VGS is less than VTH and the drain to source voltage is 0.1 volt. This is the main point. So subthreshold leakage to occur means there is some positive VDS is likely to be applied. Then only subthreshold leakage will arise. Channel is having with the both number of mobile carriers. Both number of mobile carriers means it contains electrons as well as holes. Electric field is small and the drift component of the subthreshold leakage current from drain to source is negligible because we are not applying any VDS to generate the electric field or any such much VGS. It means that VGS is less than the V threshold voltage, means electric field is very small. So as there is no electric field means there is no chance of drift current. Drift current is the current due to the drifting of carriers when an electric field is applied. Diffusion current is the diffusion of carriers. Diffusion of carriers means diffusing from one place to another place, even though there is no applied electric field. So there is no point of drifting of electrons in the channel. So therefore, unlike a strong inversion region, but in inversion region the current is due to the drifting of electrons. In weak inversion region, the current is due to diffusion of minority carriers in the channel. So subthreshold leakage conduction is dominated by the diffusion current, not the drift current. The actual current is dominated by the drift current, that is IDS. Okay. So this is a subthreshold leakage current. VGS is less than the VTH and VDS is some positive value. Source is grounded with respect to the body. So ideally there is no weak inversion in the channel, but in practically there is a weak inversion is likely to be occurred. That weak inversion contains both majority carriers and minority carriers. Minority carriers can diffuse from one place to another place because of concentration gradient that constitutes a subthreshold leakage current. So by seeing this we can understand subthreshold leakage mainly depends upon the threshold voltage of MOSFET and applied gate to source voltage VGS. So, as the threshold voltage is high, subthreshold leakage is low. As the threshold voltage is low, subthreshold leakage is more likely to be occurred. So, this purely depends upon the threshold voltage of MOSFET. So, this is a curve between the IDS. IDS means subthreshold current. Current is due to the subthreshold leakage. I am taking a semi-logarithmic axis. So, this is a VGS. As VGS is BTH, ideally there is no current, but practically there is a subthreshold leakage current. The slope of this curve is called, we can call it, this slope of this curve as subthreshold slope. Subthreshold slope. This will tell that how your device goes off when VGS is less than the threshold voltage. How speed your device will off when VGS is less than the threshold voltage. Understand the importance, the significance of subthreshold slope. This slope tells how fast your current goes to zero when VGS is less than the threshold voltage. It means that when the slope is zero, it means that your NMOS transistor is ideal. It means that subthreshold slope is zero. That means that your device will quickly off when VGS is less than the threshold voltage. If there is any slope, means your device is not quickly off when VGS is less than the threshold voltage of MOSFET. Understand the beauty of subthreshold slope. Subthreshold slope tells how fast your device will switch off when VGS is less than the threshold voltage of MOSFET. When VGS is less than the VTH, ideally the MOSFET goes off, but in practice the MOSFET will not go into off state. That constitutes a leakage current, that is a subthreshold leakage. This subthreshold slope tells how fast your device will go off when VGS is less than the VTH voltage. As subthreshold current depends mostly upon the threshold voltage, in previous slide I explained, subthreshold current is mostly upon the threshold voltage, but threshold voltage may depends upon the DABL, may depends upon the body effect, may depends upon the narrow width effect and VTH roll off. So threshold voltage depends upon these four parameters: DABL, body effect, narrow width effect, VTH roll off. What these four parameters I will explain in the next slide. So as the threshold voltage depends upon these four parameters, it means that subthreshold current also depends upon these four types of parameters. So we need to learn what these four parameters will constitute to the subthreshold leakage. Threshold voltage depends upon these four parameters. As threshold voltage depends upon this parameter, subthreshold current also depends upon this parameter, because subthreshold leakage mainly depends upon the threshold voltage of MOSFET. So we need to learn, we need to research what these four parameters before explaining the third component of leakage mechanism, which is a gate tunneling current. So before explaining this third component of leakage mechanism, that is a gate tunneling current, I want to give more information about these four concepts which constitute a subthreshold leakage. It means that still we are at subthreshold current. Still we are on the research of subthreshold current. Is everyone clear with this explanation? So, firstly, I had introduced 6 types of leakage currents in the NMOS transistor, that is I1, I2, I3, I4, I5, I6. I explained I1 current, which is a PN junction reverse biased current, and there is a BT-BT tunneling occurs when I1 current constitutes some specifications like high electric field and the two heavily doped N plus drain and P substrate. And when I am explaining about subthreshold leakage current, this is mainly because of threshold voltage, and threshold voltage is depends upon DIBL, body effect, narrow width effect, VTH roll up. So we need to learn about these 4 topics to understand more about subthreshold leakage current before going into the third component of transistor leakage mechanism, which is a gate tunneling current. Okay, still we are at I2, it means subthreshold current. Let us quickly see what is DIBL, drain induced barrier lowering. So before explaining this DIBL, I want to give some information about what is short channel, what is long channel. If the channel length is very less, that is the short channel. While designing short channel, we need to consider the second order effect like body effect, DIBL, gate induced barrier leakage, drain induced barrier lowering. All these parameters you have to take care. While reducing the channel, you need to take care about the oxide thickness, gate material, each and every concept we need to take care. So short channel means the length between source and drain is very less. Long channel means the length between source and drain is far. So let us quickly read the points in the slide. Subthreshold slope indicates how effectively the transistor goes to off state when VGS is less than VTS. This point is already explained when I explained about the subthreshold slope. This slope tells how fast your device will go to off state when VGS is less than the VTS. In long channel devices, it means the source and drain are far away. In long channel devices, the source and drains are separated far enough that their depletion regions have no effect on the potential or field pattern in most part of the design. In long channel means source is at this one, drain is at this one. Source forms a PN junction with P substrate, drain forms a PN junction with P substrate. As the PN junctions are formed, depletion regions is also formed. This formed depletion regions are one dimension depletion regions in long channel. This formed depletion regions this will not give any effect on the field generated field. Okay, in long channel, the depletion region formed between source and P substrate and drain and P substrate have no effect on the field. But in short channel, there is much effect on the field. So in long channel devices, the source and drains are separated far enough that the depletion regions have no effect on the potential or field pattern in most parts of the device. And for such devices, threshold voltage, a very good point for long channel device. Threshold voltage is virtually independent of the channel length as well as drain bias. So for long channel devices, VTH is independent. Independent means it is not proportional. Independent of channel length and drain voltage. Threshold voltage of long channel devices is independent of the length of the channel or the drain to source voltage, which constitutes a field independent of field in long channel devices. Whereas in short channel devices, the source and drain depletion width is vertical direction. It means that in 2D pattern, the depletion regions are formed in 2D way. The source drain potential has a strong effect on band bending over a significant portion of the device. It means that in short channel devices, VTH have much effect VTH have much effect on VDS, applied field VDS in short channel devices. As we increase the VDS, the threshold voltage is decreased with some factor VTH nu. VTH nu is equal to VTH minus some factor K into VDS. This equation you will find in some textbook. Okay, threshold voltage is reduced. Threshold voltage is reduced by a factor of kVDS because of as we increase the VDS. Once again, I am explaining. In long channel, the depletion regions have no effect on the field, and the threshold voltage is independent of the channel length and is independent of the applied VDS. But in short channel, the depletion regions have much effect on the VDS, and the threshold voltage is reduced by a factor of kVDS. K is DABL constant. K is a DABL constant which is having some 0.1 and 0.2 like this. Threshold voltage of short channel devices is reduced as we increase the VDS. That is called drain induced barrier lowering. Drain induced barrier lowering. Drain induced means we are inducing the drain. It means we are applying some VDS. When you are applying VDS, what happens? Your barrier height is decreased. Barrier lowering. Threshold voltage is reduced. What happens? Subthreshold current is increased. So again, the subthreshold current I2 depends upon the DABL also. Understand the point? Okay. In short channel devices, however, the source and drain depletion width in the vertical direction and the source drain potential have a strong effect on the band bending over a significant portion of the device. Therefore, threshold voltage and consequently subthreshold current of short channel device vary with the drain bias. As the drain voltage increases, threshold voltage decreases. As the threshold voltage decreases, what happens? The total current IDS increases, but subthreshold currents also increases. So barrier height is mainly depends upon the gate voltage and is not sensitive to VDS. So say for graphical I'm giving an explanation. This is a source and this is a drain. This is a source and drain. When the channel is common, it means the channel is inverted. Still there is no current because there is a barrier in between the channel. So current occur only when VDS is applied. So this is a barrier. Current is occurred only when VDS is applied. For long channel, this barrier height is independent of VDS and independent of channel length. So the point is very clear. For long channel devices, the barrier height is mainly controlled by the gate voltage, not the VDS. But in short channel, the barrier height is mainly controlled with the help of VDS, applied output voltage VDS. However, the barrier of a short channel device reduces with increase in the drain voltage, which in turn increases the subthreshold current due to lower threshold voltage. Simple point, drain induced barrier lowering. For long channel devices, threshold voltage is independent of the applied VDS, but for short channel devices, threshold voltage is depends upon the VDS. As we increase the VDS, the threshold voltage of transistor decreases. As the threshold voltage of transistor decreases, there is a possibility of subthreshold current likely to be occurred. It means that as the threshold voltage reduces, subthreshold current increases. That's all. That is the concept of DABL. Next, body effect. Body effect, as you already know, as I already explained when I am explaining about reverse biased PN junction. While designing the transistor, we need to maintain the source and drain are reverse biased with respect to the substrate. Then only your device will work. If this body should be grounded. If you increase this body voltage more negative, the threshold voltage will increase. As the threshold voltage increases, what it means? The leakage current will be decreased. If you increase this more positive, it means that threshold voltage decreases. It means that subthreshold current increases. This body effect you already know. You already have an idea about this body effect. Okay. Just quickly, I am reading this points in this slide. Reverse biasing well to source junction of a MOSFET transistor widens the bulk depletion region and increases the threshold voltage. Increasing the potential between source and body raises the threshold voltage. That is called a body effect. Okay. So this concept I already explained when I am explaining about reverse biased PN junction current. That is the first current component of leakage mechanism. Third one is narrow width effect. Narrow width effect, which will affect the threshold voltage of MOS transistor. This is a conventional MOSFET. This is a conventional MOSFET. So this is a gate, this is oxide, this is channel area, and this is the depletion region with substrate. So this is a general oxidation, normal oxidation. If you consider local oxidation, means oxide means here the oxide layer is purely planar. Here the oxide layer is not planar. Oxide layer is like this. And similarly here the gate material is planar. Here the gate is varying. This type of connection is called low pass MOSFET. Local oxide MOSFET. Local oxide semiconductor MOSFET. Low pass MOSFET. What if you design MOSFET like this? What are the effects? As you already know that the width of the gate is the width of the channel. So the decrease in the gate width modulates the threshold voltage of MOSFET. As you decrease the gate width, it will modulate the threshold voltage of MOSFET. Modulate means as the gate width changes, the threshold voltage of MOSFET changes. As the threshold voltage changes, subthreshold current also changes. That's why subthreshold current it also depends upon narrow width effect. Narrow width means your width is reduced. What happens if you are reducing the width? We will look at. Okay. There are mainly three ways that a narrow width modulates the threshold voltage. One way, second way, third way. So in low pass MOSFET means this device. This is low pass. LOPOS. Low pass. Local oxide MOSFET. This is a trench type isolation. Okay. This is local oxide isolation. This is trench isolation. This is a conventional isolation. Okay. This color is inversion layer. This color is depletion region. This is a gate material. Okay. In low pass MOSFET, depletion region spreads outside the defined channel width in the isolation area. What it finds, I will explain. In low pass, as I already explained, while forming the channel forms a depletion region. Channel forms a depletion region with the P substrate. So the depletion region formed in this low pass with the channel, the depletion region formed in the low pass that will extend into the isolation. This is a depletion region. Depletion region that will extend into the isolation area. This is the isolation area. This is the isolation area. What if the depletion region formed extend into the isolation area? This results a body depletion to increase and thereby VTH increases. It means that the depletion region is extend into the body, the depletion region is extend into the body. It means we need a more VTH to invert the channel. So VTH rises. Understand the point? So if you design your MOSFET in low-cost fashion, the channel forming depletion region is extend into the body. So as depletion region extend into the body, we need a more gate voltage to invert the channel. That is, it means that threshold voltage increases. As threshold voltage increases, what happens? Subthreshold current decreases. So subthreshold current I2 again depends upon the narrow width effect. So in this case, threshold voltage VTS increases. Now the third case, which is strength isolation. In this case, threshold voltage has not increases. It means that threshold voltage have not affected. Threshold voltage is not affected with this type of structure. So third type of isolation is strength isolation. Strength isolation is also called inverse narrow effect. This is opposite to the previous narrow effect. As you narrowing the width, the depletion region extends into the body. This constitutes a more gate voltage to invert the channel. It means that threshold voltage is increases. So the inverse operation is called a trench isolation, where we will design the transistor in this fashion, like this. This is depletion region, this is channel. Depletion region is not extend into the body. Now look depletion region up to this only. I will erase all this. So depletion region is this position, for this position only, but your body is here. So depletion region is not extend into the body. So there is no additional threshold voltage, additional gate voltage. So it means that there is no increase in the threshold voltage. I hope you clear with this explanation. Once again, I am concluding this slide. As you designing your MOSFET in low-cost fashion, LOCOS, local oscillation fashion, depletion region extend into the body. Your body started here. Depletion region extend into the body. This will constitute more gate source voltage to invert the channel. This means that threshold voltage increases. So if you design your MOSFET in this fashion, the threshold voltage should not increases. That is called trench isolation. And fourth one is effect of channel length and VTH roll-off. Fourth concept. What is VTH roll-off? Let's look at what it is. Threshold voltage of MOSFET decreases as the channel length is reduced. As I already explained, for short channel devices, threshold voltage is morely depends upon the channel length and VDS. So threshold voltage of MOSFET decreases as channel length is reduced. It means that as the channel length reduces, means we can easily invert this channel with less gate to source voltage. So threshold voltage is reduces when channel length is reduced. So the reduction of threshold voltage with the reduction of channel length is known as VTH roll-off. The reduction of VTH with reduction in the channel length is called VTH roll-off. Now look at, as the channel length is reduces, threshold voltage reduces. The channel length is increases, threshold voltage increases slightly. As the channel length increases, threshold voltage increases slightly. This is called a VTH roll-off. This time I am operating my threshold voltage with the help of channel length. I am modulating my threshold voltage with the help of channel length. As you decrease the channel length, threshold voltage decreases. As you increase the channel length, threshold voltage increases. It means because threshold voltage channel is the area between the source and drain. As the length is decreases, we need less energy to invert the channel. That is a VTH roll-off. Because VTH is depends upon the channel length. The VTH roll off means as you decrease the channel length, threshold voltage also decreases. That is called VTH roll off. As I already explained, 2D pattern, 1D pattern. For long channel devices, the field generated with the help of gate to source voltage is a 1D, whereas for short channel devices it is 2D. The principal reason behind this effect is the presence of 2D field pattern in short channel devices instead of one-dimensional pattern in long channel devices. In long channel devices, since the source and drain are far apart, their depletion regions do not have much effect on the potential profile or field pattern in most part of the channel. In the case of short channel devices, source to drain distance is comfortable to the depletion width in the vertical direction. These points I already explained when I explained about DABL concept. Okay. So we have done with the second leakage current component, that is a subthreshold leakage. We had completed with first I1 current, that is reversed bias PN junction. When I am explaining about I1, I explained BT also band to band channeling. And second component is subthreshold current, that is an I2. Subthreshold current mainly depends upon the threshold voltage, and threshold voltage is depends upon this factors: DABL, narrow width effect, body bias, VTH roll off. So obviously subthreshold leakage also depends upon this parameter. Now let us look at the third effect, which is a tunneling into the gate oxide. Tunneling into the gate oxide. So I mentioned the points related to understand the each and every concept in the slide. If you read these points, you can easily understand the concept. Okay. Now let us quickly read the points in the slide. Reduction of gate oxide thickness results in increase in the field across oxide. It means that as the SiO2 oxide thickness is reduced, it means that field is easily affected. It means field can easily travel and the effect of field is high. Okay. High electric field coupled with low oxide thickness results in tunneling of electrons from substrate to gate and also from gate to substrate through the gate oxide, resulting in gate oxide tunneling current. Now look at the point. As the thickness is reduced, I am taking lesser thickness for oxide layer SiO2. So applied gate to source voltage VGS can create a much field. So this field and lesser thickness constitute electrons can travel from gate to substrate and substrate to gate. That the current due to this leakage. The current due to this leakage is called gate oxide tunneling current. Look at the point. The high electric field coupled with the low oxide thickness results in tunneling of electrons from substrate to gate and also from gate to substrate through a gate oxide, resulting in a gate oxide tunneling current. Okay. When a positive bias is applied to the gate, due to the small, I am taking a small oxide thickness, means oxide thickness is less. Due to the small oxide thickness, which results in a small width of the potential barrier. So the electrons at the strongly inverted surface can tunnel through the SiO2 layer and then give rise to the gate current. When gate to source voltage is positive, electrons can tunnel from substrate to the gate. When gate to source voltage is negative, electrons can tunnel from gate to the substrate. These two tunneling phenomenon constitute a gate tunneling current, which is I3, the third leakage component of CMOS transistor. So tunneling can occur in both the direction. Why the tunneling is occurred? Because of small oxide thickness and higher field generation. Because of small oxide thickness and higher field generation, tunneling can occur from gate to the substrate and substrate to the gate, depends upon the applied gate voltage. If the applied gate voltage is positive, electron can tunnel from substrate to the gate. If the applied gate to source voltage is negative, electrons can tunnel from gate to the substrate. So there are basically two types of tunneling mechanism. One is flower knot-in tunneling, second one is direct tunneling. Flower knot-in tunneling, direct tunneling. Here I am taking my gate material is N plus polysilicon, this is my P substrate. Similarly N plus polysilicon, P substrate, N plus polysilicon, P substrate. There is no tunneling here. Here I am applying a positive gate voltage and I am taking my barrier. I am taking my barrier has lesser thickness. Thickness is lesser compared to this one. So the electrons in the substrate can tunnel from substrate to the gate. So similarly lesser thickness, the electrons can tunnel from gate to the substrate. So there are two types of tunneling mechanism. First one is flower knot-in tunneling, second one is direct tunneling. Flower knot-in tunneling means tunneling can occur to the triangle barrier. Here look at the barrier. Barrier is a triangle. If the barrier is triangle, the tunneling is called flower knot-in tunneling. The barrier is here. Look at the barrier. The barrier is a trapezoidal. This is a direct tunneling. In the next slide, I will explain this flower knot-in tunneling as well as direct tunneling. So this is a flower knot-in tunneling. This is a direct tunneling. Flower knot-in tunneling means the energy barrier is formed. Energy barrier formed is a triangle. Direct tunneling means the energy barrier. Here look at the energy barrier. Energy barrier is a trapezoidal. So this is a direct tunneling. So we have done with third type of leakage current, that is gate oxide tunneling current. Okay, I hope you clear why the tunneling is occurred, just because of small oxide thickness and just because of high electric field. Okay. Now fourth concept is injection of arc carriers from substrate to gate. Injection of arc carriers from substrate to gate. It means that here I am not calling tunneling. Here I am calling injection of arc carrier. Still, what is arc carrier? Why the name arc? It means that in short channel transistor, due to high electric field near SiO2 interface, in short channel transistor, due to high electric field near SiO2 interface, electrons or holes can gain sufficient energy from the field. Electrons additionally get the energy from the electric field and can inject from substrate to the gate. That is called arc carrier injection. This occurs only because of high electric field at the SiO2 interface. This is a gate material. This is a substrate, and this is SiO2. So SiO2 interface. In both SiO2 interface, the field across SiO2 interface is high. Electrons can get additional energy from the field, can sufficient energy, and electrons can inject from substrate to the gate. That is called arc carrier injection. Arc carrier injection. This effect is known as arc carrier injection. Look at the point and understand the concept. You can easily clear. If you read this plan, you can easily understand the concept. Okay. The injection from Si to SiO2 is more likely for electrons than the holes, because electrons having lesser weight than the holes. Compared to in both the particles, yes, electrons and holes, electrons are less weight compared to holes. So injection can occur more likely for electrons. So arc carrier injection means when the field across SiO2 interface, is high, the electrons and holes can get sufficient energy and can inject from substrate to the gate, can get higher amount of energy and can able to inject from substrate to the gate irrespective of any other phenomena. That is called hot electrons. When the electron gets high energy from the field, that electrons become hot electrons. So normal electron means electron doesn't get any energy from the field. Hot electrons means electrons get energy from the high energy field. So that is the fourth component of leakage. Okay, barrier height for holes is 4.5 and barrier height for electrons is 3.1. So electron barrier height is less height. So electron can freely inject than the hole, because for hole barrier height is high. So they have to cross the higher barrier height. So barrier height can be expressed in terms of electron volts. I hope you clear with this explanation. And third one is GIDL, current I5. Gate induced drain leakage. GIDL stands for gate induced drain leakage. Previously, drain induced barrier lowering, DABL. Drain induced barrier lowering, gate induced drain leakage. So there is a connection between gate and drain. Here there is no connection between gate and drain. Only drain is there. So what is GIDL? Let us look at what is GIDL. Okay. So if you fabricate like this, so this generally we need to fabricate like this. This is source, this is drain. In between source and drain we will implant gate material. But in practical we will not get this type of concentration. So in practical there is a overlap of gate with the drain and substrate. This is gate. There is a possibility of overlap. There is a possibility of overlap of gate with the drain as well as source. If you fabricate like this, so this is my gate material and this is my drain is here. My drain is here. So when your MOSFET is having in this structure, so N plus forms a depletion region with the substrate. Similarly, source also forms a depletion region with the substrate, and we are applying a gate drain voltage VDS is greater than 0 and the VGS is less than 0. It means that accumulation region. So the drain underneath the gate, the drain region underneath the gate. Okay, the drain region underneath the gate have a lesser depletion region compared to the other region. The drain region underneath the gate, have lesser depletion region compared to the other regions. Look at the depletion region. So depletion region is very low, where the drain region underneath the gate. So as the depletion region is low, electrons, there is a chance of tunneling likely to be occur to the substrate from the drain region if my VD is VDD and VG is less than 0. Once again I am explaining. Gate induced drain leakage means because of this gate. Understand the words gate induced drain leakage. Because of this gate induction, drain is leaked. Because of this induction of gate, drain is leaked. Now justify the statement in the figure. So if you fabricate the overlap of drain and gate like this, and when you apply the VGS is less than the 0, it means that the channel is accumulated of positive carriers, the channel is accumulated of positive carriers, and the depletion region underneath the gate for the drain. The depletion region underneath the gate for the drain have lesser effect compared to the other areas. So if you further increase the VD to VDD, there is minority carriers in the drain region can tunnel into the substrate. That is called gate induced drain leakage. Understand the concept. Gate region underneath the drain underneath the gate have lesser depletion region. If you increase the VD to VDD, there is a chance of tunneling of electrons from the drain to the substrate. That is called GIDL, gate induced drain leakage. Drain is leaking, means drain is lack of electrons. So let us quickly read the points in the slide. GIDL is due to high field effect in the drain junction of MOS transistor. High field effect means we are applying VDD. It means that high field effect when the gate is biased to form in the accumulation region at the silicon surface. Gate is formed at the accumulation region. As the VGS is less than the 0, it is in accumulation region. Channel is accumulated of all positive holes. Due to the presence of accumulated holes at the surface behaves like a P region more heavily doped than the substrate. So as the channel is accumulated of positive carriers, though this P region having more holes than the substrate. So it means more heavily doped. Channel is more heavily doped than the substrate. This causes the depletion region at the surface to be narrowed than the elsewhere. So depletion region is reduced. Here there is no depletion region. When the negative bias is large, means gate at 0 are negative and drain at VDD. The N plus drain regions underneath the gate can be depleted and even inverted as shown below. So here inversion layer forms. Inversion layer can enter into the drain region. Actually this is my drain region. In still drain region also there is a formation of inversion layer. So drain region is also inverted. Drain region is also inverted. From the inverted drain region, electrons can tunnel from drain to the substrate. This causes a more field crowding and peak field increase, resulting in a dramatic increasing high field effect such as valency multiplication and BT-BT. Because of this, as I already explained when I am explaining about BT-BT to occur, it means that drain and the substrate should be in reverse bias, and there is a high field across the drain. Here we are applying high field across the drain, so there is likely to be occur BT-BT, band to band tunneling can occur. Tunneling means the electrons flowing from one place to another place. So drain is leaking. Drain is leaking of electrons. As a result, all of this effect. As a result of all this effect, minority carriers are emitted in the drain region underneath the gate. Since substrate is at lower potential for minority carriers, the minority carriers that have been accumulated or formed at the drain depletion region underneath the gate are swept laterally to the substrate. So minority carriers in the drain region, can tunnel to the substrate because of high electric field at the drain, and there is no depletion region at the drain. I hope you clear with this explanation. Okay. Let us quickly explain the concept once again. If you fabricate drain underneath the gate, and we are applying accumulation region to the gate, and VDS slightly we are increasing the VDS. So if you form like this, depletion regions begin the underneath the gate have no effect on the means lesser depletion region. Even depletion region is inverted when VD is VDD. Here depletion region completely inverted, means actually this is a not channel area. This is my drain area. Drain is also inverted. From the inverted drain, if you apply VD is equals to VDD, minority carriers in the drain can tunnel to the substrate. That is called GIDL, gate induced drain leakage. Drain is leaking. because of gate underneath. That's why gate induced drain leakage. So we have done with fifth component of leakage mechanism I5. Okay. Now sixth component is punch through. Punch through means for short channel devices, the length between source and drain is very short. When you form piece of when you diffuse two n plus regions into the P substrate, there is a formation of depletion region. Depletion regions. What happens if we further reduce the channel? These depletion regions can overlap one with another. The current due to this overlap of this depletion region is called punch through. Let us look at the points. In short channel devices, due to the proximity of drain and source, the depletion regions at the drain substrate and source substrate junction extend into the channel. Depletion regions extend into the channel. This is my channel area. So the depletion region extend into the channel. As the channel length is further reduced, if the doping is kept constant, the separation between the depletion regions boundaries decreases. The separation is still reduces if you reduce the channel. As the channel length is still reducing, let us annotate with clear idea. This is my source. This is my drain. This is my source. This is my drain. This is my source. And this is my drain. Here, channel length is high. So depletion region formed with the substrate can extend into the channel. Here I am reducing my channel length to low, a bit low. Still it is extending into the channel. Here my channel length is dramatically reduces. So depletion regions can overlap. Depletion regions can a possibility of overlap. As increase in the reverse bias across the junction also pushes the junction near to each other. When the combination of channel length and reverse bias leads to the merging of depletion regions, punch through is said to have occurred. As merging of this depletion region is occurred, there is a leakage current from drain to source, that is called punch through concept I6, which is the third sixth types of leakage mechanism. Sixth types of leakage mechanism of NMOS transistor. I hope you clear with all these 6 components. Okay. Now let us look at leakage power reduction techniques. So we had studied before explaining the various leakage power reduction techniques. I had explained various types of leakage mechanism in NMOS transistor and what are the various types of leakage current, and we studied about 6 types of leakage current, I1 to I6. I1 is current due to the p-n junction reverse bias. I2 is the subthreshold leakage. Again, subthreshold leakage depends upon many parameters like GABL, narrow width effect, body bias, VTH roll-off, like that. And third one is gate tunneling effect. In gate tunneling current, we studied about slower Norden and the direct tunneling. And fourth one is odd carrier injection because of high field near the SI-SiO2 interface. And fifth one is GABL, gate induced drain leakage. Drain underneath the gate has no effect of depletion region. Because of this, if you increase the VD to VDD, there is a chance of minority carriers from drain to drain in tunnel from drain region to the substrate, that is called GADL. And sixth one is punch through. Punch through means as you reduce the channel and put the reverse bias. So there is a merging of depletion regions of source and drain, which constitute a leakage current, that is called punch through. So we studied about all these 6 types of techniques, 6 types of leakage mechanism. Now we will look at how to reduce the leakage current. There are basically 2 types of leakage mechanism. 2 types of leakage reduction technique. One is two types of leakage reduction technique. One is at process level, second is at circuit level. Means before the fabrication of NMOS transistor, before the fabrication of CMOS transistor, in how many ways we can reduce the threshold, we can reduce the sub-threshold leakage or leakage current. In how many ways we can reduce the leakage current, that is called process level. After the chip is fabricated, after the NMOS is fabricated, in how many ways in the circuit we can reduce the leakage power of a transistor, we can reduce the leakage power of a design, in how many ways, that is called circuit level technique. Process level, circuit level. Process level means at the time of fabrication, at the time of fabrication. Circuit level means when you using this component in the circuit, when you use this component in the circuit, we apply some circuit techniques, and we will reduce the leakage current. Okay, so there are basically four types of process level techniques which you already know and we already studied previously. So there are four types of process level leakage current reduction techniques, that is multi-channel doping, multi-offset CMOS, multi-channel length, multi-body bias. We already know this concept when I explained about the previous current components in leakage mechanism. What are the circuit level techniques? Transistor stacking. Transistor stacking means in transistor stacking we can conclude input vector control, and multiple VTS techniques. What are the multiple VTS? What are the various types of multiple VTS techniques? Multiple threshold, dual threshold, variable threshold CMOS, dynamic threshold CMOS, double gate dynamic threshold SOI CMOS. All these techniques we will study in the next slide. So basically there are two types of leakage reduction mechanism. One is at process level, second one is at circuit level. At the process level there are four types to reduce the leakage power. What are the four choices? Multiple channel doping, multiple offset CMOS, multiple channel length, multiple body bias. So in circuit level we had several types of techniques. One is transistor stacking, second one is multiple VTS circuit technique. In multiple VTS circuit technique there is 4 to 5 techniques: multiple threshold, dual threshold CMOS, variable threshold CMOS, dynamic threshold CMOS. Now let us look at the process level technique firstly. After that we will go into the circuit level technique. Again I prepare a very good material for this technique. If you read my slides, you can easily understand the concept at the time of examination. Okay. So multiple VTS techniques. It means that this is a leakage power reduction technique at the time of fabrication. There are 4 types of techniques: multiple channel doping, multiple offset CMOS, multiple channel length, multiple body bias. You already know what happens when your channel doping is high, when your channel doping is low. What happens when your offset thickness is low or offset thickness is high, and you already know what happens if you decrease the channel or if you increase the channel, and you already know how to bias the body. Okay, so let us look at what each technique in detail. Okay, so multiple channel doping. Multiple threshold voltage can be achieved by adjusting the channel doping densities. While fabricating, we will get multiple threshold voltage devices by adjusting the channel doping densities. By adjusting the channel doping density at the fabrication, we can get the multiple threshold, whether you will get IVT or low VT. IVT transistor having lesser leakage, low VT transistor have higher sub-threshold leakage. Okay, so at the time of fabrication we will have different density of channel doping. This requires 2 additional masks at the time of fabrication. You need to require 2 additional masks to get to get non-uniform channel doping densities. We get different threshold by non-uniform distribution of channel doping densities at the time of fabrication. That is called multiple channel doping. At the time of fabrication, we will dope the channel. Doping the channel means we will dope the body. We will dope the body. Body doping. It means if you dope the body heavily, means your threshold voltage is high. If you dope the body low, lightly, your threshold voltage may reduce. As the threshold voltage is high, what happens? What happens? You already know. Okay. This is a multiple channel doping. Second one is multiple oxide thickness. We already know as if you reducing the oxide thickness. Reducing the oxide thickness means there is high field is generated for low VGS. It means reducing the thickness means threshold voltage also reduces. We need a lesser threshold voltage, lesser gate to source voltage to form a channel. So if you fabricate higher thickness voltage, you need higher amount of VGS to form the channel. So again, high VT, low VT. High VT means lesser subthreshold current, low VT means higher subthreshold current. So depends upon your application, you can fabricate whether high oxide thickness or low oxide thickness. Now let us quickly read the slides, read the matter in the slide. Dual VTH can be achieved by depositing two different oxide thicknesses. Okay. Dual VTH can be achieved by depositing two different oxide thicknesses. For transistors in non-critical path, having higher oxide thickness results in high threshold voltage and then low subthreshold. So when you are studying about static timing analysis, you will know what is a critical path, what is a non-critical path. Critical path is the path which is having highest delay. Non-critical path which is having lesser delay. Critical path means having highest delay. For critical path, I need to reduce the subthreshold leakage. So for non-critical path, I need to reduce subthreshold leakage. How you reduce the subthreshold leakage? By applying high threshold voltage transistors in the non-critical path. So non-critical path you will have in your design, you are having non-critical path and critical path. In non-critical path, the transistors in the non-critical path have higher VTH. VTH is high. The transistors in the critical path have lesser VTH. It means that high speed, high leakage. Okay. So for transistors in the non-critical path having higher oxide thicknesses results in high threshold voltage and hence low subthreshold leakage. On the other hand, lower oxide thickness and hence lower threshold voltage in the critical path. In critical path, I am designing with lower oxide thickness. It means lower threshold voltage. It means give higher performance. In critical path, I need to get higher performance. So higher oxide thickness not only reduces the subthreshold leakage, it also reduces. So if you fabricate a transistor with the help of higher oxide thicknesses, it also not only reduces the subthreshold leakage, but also what happens? But also reduce gate oxide tunneling. When I am explaining about gate oxide tunneling, it is purely due to the thickness of the SiO2 layer. So gate oxide tunneling also exponentially decreases with increase in the oxide thicknesses. So dynamic power consumption is also decreases because of higher oxide thicknesses. How? Dynamic power consumption, since higher oxide thicknesses reduces the gate capacitance. As the thickness is high, it means that it reduces the gate capacitance, which is a beneficial for reduction of dynamic power. Dynamic power, as you already know, it depends upon the capacitance, load capacitance. So higher oxide thickness means the gate capacitance is reduced. So as the gate capacitance is reduced, which results in low dynamic power. So by using multiple oxide technique, we can also reduce the gate tunneling current, and we can also reduce the dynamic power, and we can also reduce the subthreshold leakage. This is multiple oxide thickness technique. The third one is multiple channel length. As I already explained when I am explaining about short channel effect and long channel effect. For short channel transistor, the threshold voltage decreases with decrease in channel length. This concept is called VTH roll-off. Already explained. Longer channel lengths for higher threshold transistor increases in the gate capacitance, which is a negative effect of performance and low power. For longer channel length, for long channel device, if you manufacture long channel with the higher threshold voltage, it is having some negative effect on performance as well as power. So it is in your hand to fabricate whether you go for longer channel devices or short channel devices. Depends upon the channel length, your VTH is roll off. Depends upon the channel length, your VTH is roll off. It means that as the channel length decreases, VTH is also decreases. As VTH is decreases, subthreshold leakage is increases. If you increase the channel length, VTH is also increases. As VTH is increases, there is no concept of subthreshold leakage. Lesser subthreshold leakage we will get. So depends upon your application, you will be in a position to manufacture multiple channel length transistors. So fourth one is multiple body bias technique. For bulk silicon device, the body voltage can be changed to modify the threshold voltage. At the time of fabrication itself, we can modify the body bias. So it is easier to change the body bias of partially depleted silicon on insulator devices. So go for silicon on insulator fabrication process where you can easily modify the body bias. Because body bias affect the threshold voltage, again threshold voltage affect the subthreshold current. Since SOI devices are isolated naturally. So what he is trying to say means use silicon on insulator for the fabrication of CMOS transistor, because silicon on insulators have easily controlled by the body bias effect. So these are the four types of leakage reduction techniques at the time of fabrication. Now we will look at the low power reduction, leakage power reduction technique at the circuit level. So as we already know that a single transistor constitutes a subthreshold current. Single transistor constitutes a subthreshold current from drain to source even when VGS is less than the threshold voltage of MOSFET. VGS is less than the threshold voltage of MOSFET. If you trying to put two transistors in a stacked series fashion, one transistor, second transistor, and stacked second transistor. If you are trying to put two transistors in a series of stacks, so this transistor is having subthreshold current, this transistor is having subthreshold current. Can you guess? So this subthreshold current is added to this, so this constitutes a total subthreshold current. This constitutes a total subthreshold current. Can you guess in which combination the subthreshold current is high? In this combination or in this combination? Single transistor subthreshold current is high, or the stacked series of transistor subthreshold current is high. I think you all say that, sir, because here the two transistor subthreshold current is added, so obviously this configuration is having higher subthreshold leakage current. This configuration is having lower subthreshold current, but it is a wrong concept. It is a wrong concept. Subthreshold current of single transistor is higher than the subthreshold current of stacked series of 2 transistors or 3 transistors. That is the concept of stacked series will come into the picture. Once again I am saying single transistor subthreshold current should always greater than the stacked series of more than one transistor. That is the concept of stacked series transistor. Why the subthreshold current of stacked series is less, and how to operate these 2 transistors, whether these 2 transistors in on state or whether these 2 transistors in off state. As you already know that subthreshold current will arise only when the device in off state. What when one transistor is on or when one transistor is off? What is the point of which transistor is having highest subthreshold current? Let us look what is a stacked series of transistors. Okay, so for understanding purpose, once again I am explaining. Single transistor constitutes a subthreshold current when it is operated in off state. Similarly, two stacked series of transistor when it is in off state constitute a subthreshold current that is lesser than the single transistor subthreshold current. Why it is lesser? How? What is? We will look at in the forthcoming discussion. So what is meant by stacking up transistor? Stacking up transistor means try to put 2 transistors in series, 2 same types of transistors in series. This is a stacked two stacked transistors. Okay, try to be say for example this is off state, this is off state. So for NMOS for M1 to be in off state, AB logic 0, BB logic 0, A equal to 0, B equal to 0. Then only your M1 transistor and M2 transistor will be in off state. When they are in off state, that constitutes a subthreshold current. The subthreshold current should less than the single transistor subthreshold current. Why it is less than the single transistor subthreshold current? Now let us look what happens if you put these 2 transistors in a stacked fashion. So I want to give terminal. Okay, this is a drain 1, this is a source 1, and this is a drain 2, this is a source 2. So drain 2, source 1 are at the same potential. That intermediate node I am calling as VM. Intermediate node is M. The voltage at the intermediate node is VM. If you connect these 2 transistors in this fashion, what are the effects to the circuit? Now let us look. Okay, let us quickly read the points in the slide. Subthreshold leakage current flowing through a stack of series connected transistor reduces when more than one transistor in the stack is turned off. Okay, more than one transistor in that if any one of the transistor is turned off, the subthreshold current is due to the stacking of all the transistor is lesser than the single transistor subthreshold current. Okay, this effect is known as stacking effect. It is also called self-reverse biasing. You can also note down self-reverse biasing RB. Okay, when both M1 and M2 are off, there exists some potential at VM. When M1 is off and M2 is off, there exists some potential at the intermediate node M. There should be a potential M at the intermediate node VM. Okay, positive at VM, that potential VM should be a positive potential. I think this you can observe by connecting this configuration in SPICE simulation. You will get VM as some positive value. My assignment, my sincere suggestion is to take this circuit and connect it by using the SPICE netlist and apply some input voltages that constitute M1, M2 in off state. And now look at the point at which Vm. Look at the point at which Vm and plot the Vm as a function of time. Plot the Vm as a function of time, or plot the Vm as a function of perform transient analysis. You will get the Vm curve. The Vm should be a positive. The positive voltage at the Vm. This positive voltage at the Vm affects three effects. This positive voltage at the Vm having three effects. The three effects will be explained in the next slide. Due to the positive source potential, this is my source of M1 or intermediate node MVM. Due to the positive source potential, gate to source voltage of M1 becomes negative because you are applying gate to source voltage as 0. Gate to source voltage is 0, then only it is in off state. It is in off state. So try to find the gate to source voltage 0 minus M, 0 minus Vm. So it is minus Vm. So gate to source voltage of M1 becomes negative and sub-threshold reduces, sub-threshold current reduces. At the gate to source voltage is reduces, threshold voltage is also reduces. It means that sub-threshold current also reduces. Negative gate to source voltage of M1 causes sub-threshold current of I1 to decrease. So sub-threshold current of I1 decreases. Now let us look second effect. What is the second effect? As the source is at high potential, it means that Vm is at high potential. Body to source potential of M1 becomes negative. Similarly, take body to source voltage. Take this is a body. So Vb minus Vs. Vs is some positive voltage. So similarly, body to source potential of M1 becomes also negative. As the body to source potential of M1 becomes negative, what happens? Threshold voltage is increases. As I already explained when I am explaining about body bias, if you increase more negative to the body, the VTS should be increases. As threshold voltage is increases, sub-threshold obviously reduces. So second effect is VBS is also negative. As the VBS is negative of M1, then as the VBS of M1 is negative, the threshold voltage of M1 which should rise. As the threshold voltage is rise, sub-threshold current should decreases. What is the third effect? As the Vm is greater than 0, the drain to source voltage of M1. Now observe the third effect. Drain to source. Similarly, drain to source means drain minus source. Source is at high potential, obviously a negative. So drain to source potential of M1 decreases, resulting in an increase in the DABL. When I am explaining about the DABL concept, DABL concept, as you increase the VDS, threshold voltage reduces, that causes sub-threshold leakage. As you decrease the VDS, threshold voltage increases. As the threshold voltage is increases, sub-threshold leakage decreases. So in three ways, the sub-threshold leakage is highly reduced because of the stacking effect. Sub-threshold leakage current will be highly reduced because of this stacking effect. If you connect stacked combination of transistors in this way, there is a intermediate node Vm which is at more positive at the intermediate node voltage causes three effects. First effect, gate to source voltage is negative. As the gate to source voltage is negative, sub-threshold current will be reduced. Second effect is body to source voltage. Body to source voltage is negative. It means that you are applying IVT transistor. IVT transistor means lesser leakage. Similarly, drain to source voltage is reduced. As the drain to source voltage is reduced, threshold voltage is increases. As threshold voltage is increases, sub-threshold current decreases. Simple. VGS, VDS, VBS. This is my intermediate, but which is a positive potential. S is at positive potential. Because S is at positive potential, VGS is negative. VDS is decreases, not negative, decreases. VBS is negative. As VGS decreases, subthreshold current decreases. As VBS decreases, threshold voltage increases. As threshold voltage increases, as VDS decreases, threshold voltage increases. Threshold voltage increases, it means subthreshold current decreases. Simple concept. Try to understand. If you understand the concept explained previously, you can easily grasp this concept. Stacking effect. So for this effect, these two transistors have to be in off state. So input vector should be A equal to 0 and B equal to 0. So if any one of the transistor, I already explained, not all the transistor. If any one of the transistor, for A equal to 0, B equal to 1 also, subthreshold leakage reduces. For A equal to 1, B equals 0, also subthreshold current will be reduces. If any one of the transistor in off state, any one of the transistor. In a stacking of more than one transistor, if any one of the transistor is off, the total subthreshold current of the stacked combination will be highly reduced because of there is an intermediate node is present. That intermediate node present having higher potential at the intermediate node causes VGS to be negative, VBS to be negative, and VDS to be reduced. As the VGS is reduced, threshold voltage should be increases, and this causes subthreshold leakage should be decreases. As VBS decreases, threshold voltage increases, subthreshold leakage decreases. In all the three cases, subthreshold leakage is decreases. That is the use of circuit techniques in the for leakage power reduction in standby leakage control. Okay, I hope you clear with this explanation. If you not clear with this explanation, try to look at this point after listening to the lecture and do a brief research on this concept. Okay, I hope you clear. What is stacking? Stacking of more than one transistor. The subthreshold leakage of stacking of more than one transistor is lesser than the stacking of one transistor. Stacking means any one of the transistors should be go off, because as the transistor is go off, the intermediate node having higher potential, which constitutes VGS to be negative, VBS to be negative, and VDS to be decreases. Because of these three, the three subthreshold leakage as well as VIBL is also decreases. That's all. Okay. Input vector control. As I already explained, any one of the transistors should be go off. So how to control? As this is a simple circuit having two transistors. What if the transistors are increases? How to choose the input vectors? Best input vectors. How to choose the best input vectors which gives a lower subthreshold current? All these vectors give the subthreshold current 0, 0, 0, 1, 1, 0. All these three combinations give the lesser subthreshold current, but in which the subthreshold current is much lesser. But in which input vector the subthreshold current is much lesser, that you need to find. Means taking the input vector is a serious issue. So you need to apply proper input vector. By controlling the input vectors, you can reduce the overall subthreshold leakage by controlling the input vector. So you need to choose a proper input vector. Due to the stacking effect, the subthreshold leakage current through a logic gate depends upon the applied input vector. As I already explained, any one of the transistor goes off. For any one of the transistor goes off, we have three combinations 0, 0, 0, 1, 1, 0. If you apply 1, 1, none of the transistor is off. There is no concept of leakage power reduction when both the transistors are on, because leakage power consumption is the power consumed when the device is in off state. Okay, this makes the total leakage current of circuit depending upon the state of the primary input. I already explained. Okay, state of the primary input is a main issue. The most straightforward way to find the lowest leakage input vector is to exhaustive testing. You need to go for exhaustive test. Okay, for n input we are having 2 power n combinations. For all the 2 power n combination, you need to measure the subthreshold leakage current, and you need to choose the best input vector to give the lesser subthreshold current. You need to choose the best input vector that gives the lesser subthreshold current. So for a circuit with smaller number of inputs, exhaustive method is applicable. What for a circuit with larger inputs, you need to take a randomization. Take any random input and find the subthreshold leakage current for the random vector. Okay. For larger input circuitry, random selection of input will be applicable, and evaluating the leakage of each input and keeping track of the best vector giving the minimal leakage current. I hope this point is very clear. The reduction of the standby leakage power by the application of an input vector is a very effective way of controlling the subthreshold leakage in a standby mode of operation. Yes, this is a very crucial point. The reduction of standby leakage power by applying any input vector, very effective way of controlling the subthreshold leakage. So for controlling the subthreshold leakage, the best choice to build a circuit by using stacking of transistors, and you need to choose a proper input vector that gives the lowest subthreshold current. That's all. Input vector control. For the gate